Sandeep, I think ma'am is ready, right? We shall start the program.
Yes.
Yeah. A very warm good afternoon and a hearty welcome to you all. We are honored to have Dr. Rukma Rekha Gharu, and we are extremely happy to welcome you.
This meeting is being recorded.
I, Sirisha KLS, Assistant Professor from CSE Department, welcome faculty members and students on behalf of KMIT to be a part of this one-week online workshop on privacy and cybersecurity. In today's session, let us have an overview on security and privacy on blockchain. Blockchain offers an innovative approach for storing information, executing transactions, performing functions, and establishing trust in an open environment. Many consider blockchain as a technology breakthrough for cryptography and cybersecurity, with use cases ranging from globally deployed cryptocurrency systems like Bitcoin to smart contracts, smart grids over the Internet of Things, and so forth. Although blockchain has received growing interest in both academia and industry in the recent years, the security and privacy of blockchains continue to be at the center of the debate when deploying blockchain in different applications. This session presents a comprehensive overview of the security and privacy of blockchain. I am delighted to have the gracious presence of our today's resource person, Dr. Rukma Rekha Gharu, Associate Professor, School of Computer and Information Sciences, University of Hyderabad. Dr. Rekha Gharu has received her PhD from Andhra University in the year 2015. She has expertise in the fields of cryptography, information security, pervasive computing. She has lifetime membership in Cryptology Research Society of India. She has published various papers in many international journals too. Ma'am, it's an honor to welcome you on behalf of the organizing team of KMIT. Without any further delay, I would like to hand over the session to Rukma Rekha Gharu. Over to you, ma'am.
Thank you, Sirisha. Thank you very much. I hope you are able to see my screen.
Yes, ma'am. Yes, ma'am. It's visible.
Okay. Thank you so much.
Yes, ma'am. Yes, ma'am.
Thank you. Okay, right. So, good afternoon, everybody. A warm welcome to all of you. The average attention span of a human being is supposed to be 17 minutes. And I think post-lunch it will reduce a little less than 17 minutes. And we got a 3 hours session now. So let us see how far we can succeed in getting your attention. So welcome to the session on security and privacy challenges in blockchain. I'm sure you had a session on blockchains yesterday. Before starting and going into the security and privacy challenges, I'd like to give you a glimpse of another world of blockchain, the blockchain that you have discussed, that you have shared knowledge yesterday is a typical scenario or, through which blockchain have become public, the Bitcoin blockchain. Yes, that is the Bitcoin. Bitcoin is the product that have broad blockchain platform into to make it more popular and all. But then we moved beyond Bitcoin. It's not that blockchain. There is a time where blockchain and Bitcoin are thought being as synonyms. So you talk with Bitcoins, people relate them to blockchains, and blockchains relate to Bitcoins. They are so interrelated with each other that people consider them to be synonyms. And then a little later, after the Bitcoin transactions and all, a second generation of blockchains have developed, where people started looking into the advantages of blockchains beyond cryptocurrency transaction. Yeah, blockchains are very much useful in cryptocurrency transactions, but the advantages of blockchains go beyond cryptocurrency transactions. And because of that reason, now blockchains are being adapted by almost every organization. Right. I'll talk about that a little later in the talk. Some of the slides are maybe an overlap of yesterday's talk. We'll try to skip those slides and move on. So this is the outline of my talk, where we will see the building blocks of blockchain, the blockchain architecture, how you visualize blockchain in an architectural point of view, and various types of blockchains, some of the consensus algorithms used in blockchains applications, and then come to the core part of our talk, which is the challenges in blockchain, where we focus. There are many challenges in blockchain, where we focus will be more on security and privacy issues in blockchain. So when it comes to the building blocks of blockchain, hash function is one major building block. Most of the part of blockchain transactions are validated using these cryptographic hash functions, where there are many hash functions available in the mathematical world, but we choose cryptographic hash functions in blockchains, where I'm sure a hash function is already defined in the last session, so we'll only focus on those properties which are more helpful for us. The first property is the collision resistance. Collision resistance property is that property where two different inputs will give you the same hash value. If you are able to find out two such inputs which will give you the same hash value, then there is a collision in your hash function. So what is the hash function used in Bitcoin blockchain? SHA-256 algorithm, right? So SHA-256 algorithm is that algorithm where the input can be of any size, but the output is a fixed size input, which is 256 bits. The hash value is 256 bits. Imagine, is it difficult or is it not possible theoretically to find such a collision? Yes, theoretically it is possible to find such a collision. It is because your input can be of any size, whereas the possible output is only a 256 bit value. And if you consider only zeros and ones as possible inputs and outputs, then for such binary value, the possible hash values can be, the possible combinations can be 2 power 256 values, right? Which is a number less compared to the infinite set of our input. Input is any size input. We are not having any restriction on the size of the input. So your input size is almost infinite, whereas your output size is fixed to 2 power 256 possible options, and it is possible to find a collision theoretically. But SHA-256 algorithm is that algorithm which ensures collision resistance, in the sense that it is almost infeasible to find such a pair of inputs x and y which will give us to the same hash value. And then comes the second property, hiding property, where in this hiding property, when a secret value r is chosen and appended to your input x, whatever hash value that you get from them, it is difficult to find the x value, in the sense, when you combine, why should we do that? When we come to proof of work, we will see that it is difficult to find x when you have this hash value, because that is what you do in proof of work. If you realize yesterday, you will find, you are supposed to find that nonce value, right, which is concatenated with the hash of the other transactions. And because of this hiding property, it is almost infeasible to find value of x. And the Puzzle friendliness. Puzzle friendliness is that you, when you have again here the hash function h, whatever hash function in our Bitcoin blockchain, the hash function is SHA-256 is said to be puzzle friendly, where for every n-bit output value, the n-bit output value we are referring here is the 256. So our n is here 256 in the context of Bitcoin blockchain. If some value k is chosen with some high minimum entropy, it is difficult or it is infeasible to find x such that the hash of the combination of k and x is equal to y in a certain period of time. We said it is in a certain period of time because considering 2 power 2 n bit is 256, right? So you have to find all possible combinations, which literally leads to your brute force attack, and that is the reason proof of work is so difficult in Bitcoin blockchains. Next, coming to hash function. Next to hash function, digital signatures are the most used cryptographic algorithms in bit blockchains. I'm not talking about Bitcoins now. I'm talking about blockchains. So where we have three different algorithms. One algorithm generates the keys, second algorithm generates a signature, and third is a verification algorithm which will verify if your algorithm is valid or not. So there will be a property that will be given for the verification of your signature, and if that property is true, the verification will hold that property, and if this verification is true, your signature is valid, and the signatures, especially signatures used in blockchains, are existentially unforgeable, in the sense you cannot forge a signature. And every node that initiates a transaction in blockchain network will be using these digital signatures for every transaction that they make on the blockchain. So one is hash function, the second is digital signatures, the third one is public key infrastructure. Public key infrastructure is that infrastructure where every node in the network will have a pair of keys known as a public key and a private key. Generally, the private key is generated by the node and from which the public key is calculated. And we establish a binding in such a way that there will be some relationship between the original identity of the node. Node can be the user, the system that we are referring to. And when we are using this public key infrastructure to manage the keys, we try to establish a relationship between the original identity of the node and the public key with the help of certificate authority. This happens in that in such a way that I generate my own private key. Private key can be something like my secret key, my password, my very specific thing which is known only to me. I can share it to the certificate authority saying this is my private key. The certificate authority will provide you the respective public key where there is a relationship established between the private and public keys in such a way that when you sign a particular message using your private key, it is verified using your public key. So the signature which was done using your private key is equivalent to the verification that was done using your public key because of the relationship that holds between the identity and the public key. So basically your signature verification leads to your identity verification. But does it lead to the original identity verification? No, because blockchains, we don't use original identity, especially Bitcoin blockchains, we don't use original identities. We all are identified only by our public key addresses. But then the usage of blockchain boundaries have expanded beyond the origins of Bitcoin. Now people have started using it in different domains, in different applications. So I can use it in my organization, I can use it in a healthcare domain, I can use it in IoT, cloud computing, you name any application, we can find a scenario where we can use blockchains. So now the definition of identity verification has changed. Bitcoin strongly suggested or recommended for an anonymous usage. That's the baseline on which Bitcoin blockchain have developed. But now when we are using it in a healthcare domain and all, the definition of identity altogether have changed. So blockchain allows the key pairs to be generated by users themselves, which are called as addresses in Bitcoins, but in other blockchains such as Ethereum blockchain and what you call Hyperledger Fabric and all these blockchains, we don't call them as addresses, we call them as credentials, where it can be a private key, public key paid, or a password and an ID combination. It can be a pair where one is secret and the other is made public. And because no central management of public keys is there, the identities have become pseudonyms because they are. It is not that one single user will be giving these scenarios. You look at Bitcoins, nobody is maintaining these public keys, which is, and then you look at Hyperledger Fabric, there is a certificate authority which will maintain them. So we really don't call it as completely anonymous, but we call it as sort of pseudonymous because we have some trust on that, what you call, on the membership service provider, which is there in Hyperledger Fabric. So revisiting the definition of blockchain that was already discussed yesterday, see, before going into the other building blocks of blockchain, what is it that blockchain is made up of? Is it a revolutionary technology? Is it something that came miraculously into this computer science world? Or is it an extension of something that was already there in the computer science, what you call, into the computer science world? So you look at blockchain. Blockchain is a very beautiful amalgamation of the existing technologies that are there in computer science, right? Almost nothing is new in blockchains. You take any topic, there is you look at hash functions, you look at digital signatures, you look at ledger maintenance, you look at the proof of work that was discussed. Nothing is new in blockchains. Everything was there in computer science centuries ago. Cryptographic hash functions are very old functions. Digital signatures are much older functions. Ledger maintenance, any database person knows how to maintain a ledger. Right? Distributed ledgers, computer science people, we all know how distributed systems function, how we manage things in distributed things. So what is it? So distributed systems is already there. Cryptographic primitives are already there. Decentralized P2P networks are already there in computer science. So what is new in blockchain? What is that new technology that made overnight blockchain a hot cake in this computer science world? Why everybody is going gaga over this word of blockchain? Why everybody is thinking that blockchain is the new trend now? Is it some new technology that addresses every problem of computer science? No. Right. Blockchain is, as I said, a beautiful amalgamation of these technologies to achieve very specific targets. Please do not be under the belief, especially students and research scholars who are looking for research directions. Please do not be under the assumption that blockchain is a solution for all the problems in computer science. Blockchain addresses very specific problems in a very decent and very, in a very nice fashion. But if you think this is the only solution for every problem in blockchain, you are mistaken. Right? So let us see what are all those problems that blockchain addresses and what are those things that we can expect from blockchain. Blockchain, as you all know, is a public ledger in which all the committed transactions are stored in chain of blocks. So this is how a blockchain thinks. We have blockchain functions where you have a number of blocks. A new block keeps adding to this chain, and because each block is connected to the other block through a chain, what does that chain holds? I'll let you know. And each block contains committed transactions. So we all know what a committed transaction is. A committed transaction is is that transaction which is done and there is no way of which is made permanent in your database. Right. So this is what each block contains. Please excuse me if you have already seen these slides in the previous presentation or in the last presentations. But this is what your entire block. So I have seen 3 blocks in this presentation. And you know, each block is divided into 2 parts. One is the header part and the other is the transactions part. Transactions part is that part which is represented in yellow color, where you contain the records of transactions. So if you see in block 1, you have 3 transactions followed by some more represented by dots. Similarly, block 2, block 3. And apart from the transactions, each block will have some header information, where the header information contains many things, of which one is, it contains the hash of the previous block. If you look at block 2 header, it contains the hash of block 1 header and the hash of block 2 transactions. So if block 2 contains 20 transactions, the hash of all these transactions, the cryptographic hash of all these transactions put together is a value that is stored in block 2 header. Apart from this value, the hash of block 1 header is also stored in block 2 header. So imagine, why should I, because of this, you get the chain link between the blocks. Let me tell you what will happen if I try to change. We have been saying, right? Once a transaction was committed and kept in a block, you cannot change it. It is tamper resistant. Why are we saying, why is it so difficult? Can I not simply access the block, edit the transaction and say the transaction is done? Why is it so difficult to change a transaction, to alter a transaction in a blockchain? Imagine this scenario where, please have a look at the block 3 header. Block 3 header contains hash of block 3 transactions and hash of block 2 header. So if I change a particular transaction in, say, for example, block 1, the transaction B76, if I change this transaction, what happens is that when I change this transaction, suppose say this transaction is supposed to be a transaction between X and Y, I modified the transaction as X, that happened between X and A. The receiver of that particular transaction was modified from Y to A. As a result, what will happen? The hash of block 1 transactions will be modified because one transaction is altered here. This hash value changes. As a result, this entire hash value changes, which is stored in block 2 header. As a result, this entire hash value changes and which is stored in block 3. So if one transaction that you have modified in block 1 will have a ripple effect on block 2 and so on to block 3 and so on to the subsequent blocks. As a result, what happens? These blocks will not be verified by the respective users. Thereby, if your block was not verified and validated, it becomes an invalid block. Thereby, it will not be added into the block or it will not have weight in the blockchain. So each block points to the previous block by a hash value, which is known as the parent block. So for block 3, block 2 is parent, block 2, block 1 is parent. Block 0 is always called as the genesis block. Apart from the parent block, we have different names known as uncle block, orphan block and all. As the slides move on, we will refer to them. So I'm sure this is definitely something that was considered yesterday about what is a block structure and block header. I'll skip them and come to the next building block of our blockchains, which is Merkle trees. Merkle tree is again a concept which was there in what you call computer science world since a long time. And Merkle root, I'm sure you have had a discussion on how to calculate Merkle root and all. The beauty of this Merkle tree concept is that you change a particular transaction, all the way the entire Merkle root gets changed. And don't think that if I make a alteration or if I change a transaction in blockchain, that effect will be limited to that block or to that transaction, or it is not the alteration or the change that you made will not be local. It will have a ripple effect to all the subsequent blocks. So thereby every block gets nullified. How does this function is that this blockchain, the committed transactions will be added to the blockchain, and all that block, which is a distributed ledger, will be shared on the on a public portal. So it is something like in the network, all of us, suppose say some 100 people are there in this meeting. All 100 of us are connected through a blockchain where every one of us can have a copy of the blockchain. Right. Hopefully I'll come to that part how this transaction happens. But imagine if you want to change transaction C, h of C changes, thereby this value changes, h of C plus h of D, and thereby the root value also changes. So it is a binary search tree where the tree nodes are linked to one another using hash pointers, and this entire thing is organized as a Merkle tree, and the Merkle root which is there at the top is used to construct the block hash. As I told you, if you change a single transaction need not be you will modify the entire transaction. You will change what you call a single bit of the transaction. I'm not saying even a letter or a word or a character. I'm saying a single bit of the transaction. You need to change all the subsequent block hashes. Hashes has this beautiful property, cryptographic hashes known as Avalanche Effect. What does Avalanche Effect says is that if you change a single bit of the input, it will have more than 50% of the bits will be changed in the output. Suppose say there is some 256 bit input and a 256 bit output, and if I change one single bit in the input, according to the Avalanche effect property, the output will be differed by at least 128 bits. So it's altogether a new value. Right? So because of that thing, changing a transaction in a blockchain is highly impossible. Let us see how people visualize blockchain. There is no standard representation of blockchain, or there is no standard architecture for blockchain, but different people started using uh, blockchain in different visualizing blockchain in different layers. So this is that one standard blockchain architecture where we can relate this layer to the network layer that we to the OSM model that we standardly study. Where when you so this is easy to map also as well. So when you look here, the data layer contains the data blocks, the original transactions, the hash functions, Merkle tree, the chain structure linked by the hash values, the digital signatures, and the timestamps. Why do we need timestamps? That we'll discuss when we have a security, when we look into the security issues. Then comes the network layer. In the network layer, blockchains use P2P network, and apart from that, to communicate with other nodes in the network, they use a transmission protocol known as gossip protocol, which is very popular in the networks, and have certain verification mechanisms to identify the other nodes in the network. So these are all the things that we have in network layers. But because this work, you don't have a centralized node or a centralized authority to watch over all the nodes in the network. there should be some consensus in which people have to reach some consensus to on a particular transaction. You need to agree on something through some mechanism. This is what consensus means. So proof of work is one popular consensus mechanism that is used in Bitcoin blockchain. But as I said, people have started looking the advantages of blockchain beyond Bitcoin. So we have many other blockchains such as Ethereum, Hyperledger Fabric, Ripple, Corda. Hyperledger itself have number of variants in its blockchains for various purposes. So all of them started using, considering the usage, considering the convenience, people have started more using various consensus algorithms, proof of stake, delegated proof of stake, practical Byzantine fault tolerance, and many other consensus algorithms. So what consensus algorithm you want to keep in your blockchain depends on what is the type of your blockchain, for what purpose you are going to use your blockchain, what are the nodes in the blockchain. In the sense, you basically have three types of blockchains, public blockchains, permission blockchains, and consortium blockchains. So public blockchains are those blockchains. One example is Bitcoin blockchain is a public blockchain. As the name says, anyone from the public can be part of the blockchain. I can join Bitcoin blockchain, you can join Bitcoin blockchain. We all can buy Bitcoins, we all can sell Bitcoins, we can do a send transaction, we can do a receive transaction. We can be part of the consensus as well in Bitcoin blockchain. Then we have permission blockchains, where compared to public blockchains are also known as permissionless blockchains. Then we have permission blockchains, where you need permission to be part of the blockchains. Suppose, say, all of a sudden KMIT has started, have thought of using a blockchain to give certificates, degree certificates for its students, right? Yeah, it can be made as a public blockchain, but why do you need the entire world to see what is happening in KMIT? So who can be part of KMIT? Probably the stakeholders, the students, faculty, management, and probably a few other people who can be part of that particular network. So these people who are tightly connected with each other, there is a relation between the management and the students in certain perspectives, management and faculty in certain perspectives, faculty and students in many perspectives, right? So these people can be part of the network, where a permission blockchain functions very well for them. You can be part of that blockchain, and you need permission to you need to have a permission to enter into that network, and that permission is given by a membership service, right? So you get that membership for that particular blockchain, and you be part of the blockchain. You can do some transactions. However, compared to public blockchain, what you can do on the permission blockchain are slightly limited, right? So depending on what is the type of blockchain that you use, your consensus mechanisms vary. Then you have an incentive layer. Incentive layer is that layer once this mining and all happens, and when the block gets added to the blockchain, what is the currency mechanism that you relate to in your architecture? How are you going to issue the currency? How are you going to distribute the currency? For example, after every block is added to the Bitcoin blockchain, the miner gets a reward of 6.25 Bitcoins as of now. Earlier it used to be 50, after some time it was 25, 12, and now 6.25. 6. So then Ethereum blockchain is another blockchain where Ether is the currency that was used. So how do you distribute ethers? How do you buy ethers? There is also this concept of burning ethers when your transaction need to be validated. All these things will be part of your incentive layer. Yes, is there a question? Okay. So I'll continue. Then the contract layer. Contract layer is something which maybe you haven't seen in the previous session, where this refers to the smart contracts that are introduced in the second generation of blockchains. Bitcoins do not have the concept of smart contracts, but when the usage of blockchain was extended to enterprises and organizations, the business agreements and policies need to be written into a smart code, into a smart logic and executed on some machine of the blockchain, which is referred as the smart contract. So the script code, the algorithm and functionality of the smart contract all deal with the contract layer. Finally, where are you going to use this blockchain architecture? We can use it for cryptocurrency. I can use it for financial trade. I can use it for healthcare domain. I can use it in cloud computing. I can use it in IoT. You name any application. We can use blockchain architecture considering the features that we have in that. This is another representation of blockchain architecture where you can now you can relate probably a simpler way. So all the blue dots represent the various nodes in the network that are connected. So what happens, this node, if it wants to propagate some information, suppose say this blue node wants to propagate some information, it will pass on to the nodes it is connected to. So it will pass on to this node, and this node. This node will take the responsibility of passing on to its connected nodes, and this will take the responsibility of passing the, will not say passing, but propagating is what we say in blockchain. That's how entire information is propagated to all the nodes in the network. And once a particular transaction or a block is validated and accepted by all the nodes in the network, it is added in the global ledger. This global ledger is accessed by all the nodes in the network. Anybody can verify the transactions that are there in the blocks of the blockchain. However, can you add a transaction to that block? If it is Bitcoin, yes, anyone can add a transaction to the block in a blockchain. But if it is a permission blockchain, your permissions are restricted, and depending on the role you play, you are either allowed to add the transactions, or you are only allowed to read and verify the transactions. And finally, the applications. Now, number of blockchains came. So Hyperledger, Ethereum, Bitcoin, all these are various blockchains that are used. Bitcoin is exclusively for cryptocurrency transactions. But as I told you, the usage of blockchain have expanded beyond cryptocurrency. So I'll just revisit the blockchain transaction process. More or less, it is the same in all the blockchains, except that certain few changes are there between a public blockchain and a permission blockchain. So what happens in this blockchain transaction process is that all the nodes that are there in the blockchain, many transactions do happen, and when these transactions happen, all the miners, whoever are interested in the what you call, suppose say, okay, I'll give you an example. Suppose say there are 100 nodes in the network. So the transactions are, I make it, so node 1 makes a transaction to node 5, node 7 makes a transaction to node 11, different nodes make transactions to different other nodes. So the transaction can be send currency, receive currency, it can be anything. So all the transactions that happen in a certain period of time are stored in something in a pool, which is known as unconfirmed transaction pool. And these transactions are propagated on the blockchain network by using a protocol known as gossip protocol. As I told you, one node propagates the transactions that are available to that node to the nodes connected to it. The nodes connected to it will take the responsibility of propagating those transactions to the other nodes of the network. Right? So that's how gossip protocol works. And what happens, the adjacent nodes or the peer nodes is what we call. The peer nodes validate these transactions. How do they validate these transactions? Every transaction that was done by me will be will be signed or will be stamped with my digital signature, where I sign the transaction using my private key. Any peer node in the network can validate the transaction using my public key, which is almost public. My public key is known to all the nodes in the network. And additional to that, there is some preset criteria that is included. Different blockchains follow different preset criteria, and that is included in the block. When these two conditions are satisfied, your transaction is validated. So after that, these peers will use their computational power to mine and become block miners. So what do these miner nodes do is that they collect all these transactions, make a block. So every block has certain limits. Say some blocks have a limit of 100 transactions per block. Some blocks have a limit on the size of the transaction, size of the block. Different blockchains follow different criteria. So suiting that criteria, they will pool all the transactions from that unconfirmed transaction pool, form a block, and then for that block, there will be a computational puzzle that will be given by the network. Every miner will be having his own block. Suppose say miner 1 have transactions 7, 8, 10 in his block. The miner 2 may have 7, 11 and 15, and miner 3 may have altogether a different set of transactions. So each miner will try to solve the computational puzzle, and who can solve the puzzle first will become the winner of that particular uh, uh, puzzle solving process, and they will be able to create a new block. In the sense, whatever block that they have created will be added to the blockchain. The other people who have pulled some transactions, they will again go back to the unconfirmed transaction pool. And again, this process repeats. But for the winner, there will be an incentive where small amount of incentive is given for creating that new block and adding one more block to the blockchain. So once that particular block is formed, and this new block will be added to the existing chain, and the transaction is confirmed, you know how the new block will be linking to the previous block using the cryptographic hash pointers and all. And you know, a transaction needs a minimum of 6 confirmations in the network to be considered final. Like, why do we need 6 confirmations? Why can't we make it as one single confirmation? See, a transaction, when it was being validated by the peers, it gets confirmation 1. A transaction, once it gets to the miner, it will get confirmation 2. Once it's part of the confirmed block, it gets confirmation 3. And this block will need to have 3 more confirmations to make sure that it is permanent in the blockchain. Because your block can be an orphan block, and if your block is an orphan block, there may be a chance that your transactions may go back to the unconfirmed transaction pool. What is an orphan block? Orphan block is that block where in a network there will be a possibility that 2 blocks are formed at the same instance. How can 2 blocks form? What is our condition to form a block is that the miner who can solve the puzzle first will become winner, and his block will be added. What if we have 2 winners? What if 2 people are able to solve the puzzle at the same point of time? Then there will be a split in your block. Whatever blockchain that you are seeing is an ideal scenario. In a real-time scenario, this is not what it will look like. So you have block 1, block 2, block 3, block 4, and block n. This is a very ideal scenario. But what happens is that you have block 1, block 2, block 3. Block 3 is split into 3A, 3B. Some people start adding blocks to 3A, some people start adding to blocks 3B. We call it as a fork in blockchains, right? So whichever network or whichever link of that fork gets expanded faster, whichever chain have more number of blocks, that will become a public one, and the other one gets terminated, and it will again move back to the unconfirmed transaction pool. That is the reason you need 6 transactions at least for your transaction to be final. I'll skip these characteristics of blockchain. We already had enough introduction to blockchain. But this is another thing: public blockchains, private blockchains, consortium blockchains. I already told you a little bit about this, where this is open to anyone. Any participant can join in the decision making. Bitcoins are a great example for public blockchains. Another example, Ethereum blockchain. Private blockchains, only one organization can form a network. So my own university wants to form a network. Private blockchain is a great example. Okay, where any member of my network or organization can have read access to all the transactions. They can verify a transaction, they can read a transaction. But to write a transaction onto the blockchain, you need to have restricted access. Not everyone can write a transaction onto the blockchain. You have restricted access. Consortium blockchain is that thing. Suppose suppose KMIT college itself have some branches, 2-3 branches. Then individual branches, but all these 3 branches work together. Then there is a consortium blockchain where more than one organization come together to form a network. Read permission is again open to all within the network. However, write permissions are constrained. You will be given to only specific people from each block, from each organization. This is something which we don't need, but yeah. See, consensus algorithms, there are various consensus algorithms used in various blockchains. Proof of work is one popular consensus algorithms because it was used in Bitcoins, one reason. And the complexity of proof of work is very high. Probably you got to know about the complexity of proof of work in the last session itself. Right? Finding out this nonce that satisfies this entire condition is so difficult. You don't have you don't have an intelligent way of finding that nonce. The only way that you can find out that nonce is brute force. So I need to find out some value which satisfies these conditions, and I don't have an algorithm, I don't have a formula, I don't have some intelligent way to find out that value. The only way that I can find out that value is brute force. And what do? I use all possible mechanisms, all possible fastest way of figuring out the numbers. So I use application specific integrated chips, I use FPGAs and all to find out that numbers. So what is it that happens here is that once that nonce is obtained, that is the miner will be broadcasting the nonce, and in the proof of work, calculating the nonce is a very tough job, whereas verifying the nonce is an easy job. So and one more possible thing that can happen here is that when multiple nodes find the nonce at the same time, when you have multiple winners at the same time, branches or forks may be generated. In a proof of work chain, what happens here is that the miner will be receiving a reward. What is it? The miner, why are miners so hungry to become the winner of this block? What will they get as an incentive? What is their goal? The incentive that they get is some bitcoins, which is, as I told you earlier, when the Bitcoin blockchain have started, it was 50 bitcoins as a reward. And then the difficulty level have increased and the bitcoins have decreased. That is again a strategy that was being implemented. So after certain point, the number of rewards have reduced to 25 bitcoins, and then it was reduced to 12.5 bitcoins, and right now the reward is 6.25 bitcoins. Apart from that reward, the miner is entitled to the transaction fees. Suppose, say, if a miner mines a block which contains some 50 transactions. Each transaction will have certain amount of transaction fee. And what are the transaction fees entitled for all those 50 transactions will be given to the winner of that particular block. So that is another incentive that he gets. Eventually, this reward, Bitcoin reward, will fade away slowly, because this 12.5 have already reduced to 6.25. Slowly, it will become 3.125 or something. It doesn't have any value, and then it will further gets halved after your difficulty increases a little. But most of the miners will be looking for the transaction fee that will be there in the block, transactions of the respective block. So the rule is that once the block rewards, so the block reward is halved after every 210,000 blocks. So that is basically 21 million. This is the strategy that was given by Satoshi Nakamoto when he have introduced Bitcoin blockchain. And once your reward becomes zero, the miners will get only the transaction fees. Then we have one more consensus algorithm, proof of stake. Proof of stake is an energy saving alternative to proof of work. Why did I say energy saving alternative is that? If you know what proof of work what is it that we are doing in proof of work is that we are wasting enormous amount of energy and computational resources to find out some random value which we are calling as nonce. Okay, once that is added, somebody will get the reward, somebody the winner will get the transaction fee, fine. But what is it, what about that computational power? What is it that you are doing it? China is leaving lot of carbon footprints, because that is a place where lot of mining is happening, Bitcoin mining is happening. And then definitely environmental conservatives do not like that idea of proof of work because of the carbon footprints, the amount of energy that was being consumed, power that was being consumed, and the computational resources that are being, you use lots of FPGAs which run at very high speed to find out that nonce. Hardly you have 10 minutes time, and nobody will be waiting the entire 10 minutes to find out that nonce. Right. The first one is the winner. So the sooner the better. So people are looking for alternative to proof of work. Proof of stake is an energy saving alternative. Where what is proof of stake? How does this work? See, what is it that you do in proof of work is you work on your nonce value and you provide the proof by providing the value, saying I have worked with for this nonce and my nonce is validated in the puzzle given. Whereas in proof of stake, you provide the proof of the ownership of the stakes that you hold in that particular network. What do you mean by stakes? When I refer to stakes, I refer to the amount of coins. Those coins can be Bitcoins, those can be Ether coins. Anyhow, Bitcoins opted for proof of work, so we don't work on that. But we are trying to use this proof of stake in other blockchains. So every blockchain have its own currency, right? So what is the stake that you have in that network? So the idea is that if there are 100 nodes in the network and a particular node have more amount of stakes in the network, that particular node will be given more priority to add a block into the blockchain. What is the idea behind it? That when he has more stakes in the network, the chances that he will attack the network will be less likely. It's obvious, right? When I invest more in a particular thing, I don't want that particular network to be attacked or to be destroyed. However, the disadvantage is that if you are giving blocks rewards to already to that person who is having more stakes in the network, it is basically the rich getting richer. So to avoid that disadvantage, there is a combination that was added. Obviously, the combination was along with the person who has highest stakes, we add one more parameter saying who have old age coins, in the sense the tenure through which they have hold those coins. If I am having these stakes for a long amount of time, it was considered as a honest person in the network, or the regular person who is there, who is part of the network and who did not join the network just to add his block. So many blockchains adopt proof of work at the beginning, but now slowly they are transforming to proof of stake, where the mining cost is nearly zero. Ethereum is planning to move from ET hash, which ET hash is a proof of work algorithm used by Ethereum. Now from ET hash, Ethereum is planning to move to Casper, which is proof of stake algorithm. And to combine, apart from proof of work, we have also another different modes of proofs available. Proof of activity is proposed. Proof of activity, what is it that it says? A mined block, if at all to be accepted and validated and to be added in the blockchain, it need to be signed by n minus. So what is that n? It could be 50% of your entire network, 1/3 of your entire network. It depends, right? So then we have, that is proof of activity. So this many number of miners need to activate that particular block to get added to the network. Proof of capacity, again, miners need to allocate large hard drive space to mine the block. Many things are there: proof of importance, proof of storage, proof of deposit. You deposit certain coins into the network and then your block will be added into the network, and that deposit will be held for certain amount of time, and then it will be refunded to you. You give some proof of storage. Dr. Subbarao yesterday have asked me to convey that yesterday there was this question of proof of personhood also. Yeah, proof of personhood is slightly different than all these proofs. The only difference is that in all these proofs, you can have more than one account. In a Bitcoin blockchain, in Ethereum blockchain, you can have more than one account. So you can be part of mining in 2 different wallets, or in 2 different accounts, or 4 different accounts, or 6 different accounts. But then proof of personhood is that particular consensus algorithm where the proof is given based on the validation of an individual user. So how do you validate an individual user? Probably his biometric identification, or some social security number, or a Aadhaar number, where you can uniquely identify a user. So this proof of personhood is more useful in applications like voting application, where you need the personhood representation in the respective consensus algorithm. Then we have delegated proof of stake. Delegated proof of stake is that particular thing. It is slightly an extension to proof of stake, where obviously whoever is having highest number of stakes will get a chance to add their block. However, rather than all the nodes to participate in the network, see, if all the nodes start participating in the mining process, that will become a very slow process that we have already seen in proof of work. If 100 nodes need to come to consensus, it is very difficult to come to consensus. So what this delegated proof of stake did is that they elect their delegates to generate and validate a block by process of voting. So not every stakeholder in the network will participate in the process of mining. Only the delegates who are elected. Right, so for 100 nodes, there can be some 5 delegates or 6 delegates depending on the numbers. So how do you elect these delegates? Based on the proof of stakes that they have. If a person have more number of stakes, he could be possibly elected as a leader or a delegate is what we call. These elected nodes, then they form a set. So these 5 nodes or 6 nodes, they form a set, and then they propose a block and validate the data state. So, and it's not that these delegates are permanent. Once that block is added, in the next block, again, you need to elect your delegate. So they took turns on voting for blocks on behalf of their stakeholders and validate their previous authenticities. The problem is that the problem we generally identify with proof of stake is that if a rich person, a person who is having more number of stakes, is again adding a block, he will again have to he will again be getting the reward and he will be becoming much richer. To avoid that, as I told you, we will be adding the age of the coin and all. But apart from that, the other thing that Ethereum have introduced is that if my transaction has to be validated, I have to invest something. Because I'm not using proof of work, I have to invest something. What is it that I invest is that, what is it? What does Ethereum blockchain say is that you burn some of your ethers. I have some ethers in my wallet. You burn some of your ethers to get my transaction validated. So it is not really that the rich always gets richer, because they will be burning some of their coins also while their transactions are getting validated. So the advantages of delegated proof of stake is that you have fewer participants for block validation, because only the elected delegates will participate in the block validation. Thereby, your block confirmation will happen quickly. Dishonest delegates could be voted out easily, because if they try to attack the network, obviously their stakes will also be in risk. So it will be easy to delegate out your dishonest delegates, to vote out your dishonest delegates, because election of the delegates happens on a voting basis. Only thing here, the limitation of delegated proof of stake and proof of stake as well, is that slowly this will lead to a centralization tendency, where we started the idea of blockchain saying it is a decentralized one. We are again moving to the centralized tendency, because you start electing person with higher stakes, and if it becomes close to a centralized fashion, then it will again be a centralized network where blockchain loses its flavor. Then we have practical Byzantine fault tolerance, where we have many algorithms in this Byzantine fault tolerance zone, where a primary node will be selected according to some rules that are decided in the network, and they will be responsible for ordering the transaction. What is ordering the transaction? Ordering the transaction is that when a number of nodes are doing transactions in a network, the miner's job is, this doesn't apply, please don't visualize it in a Bitcoin scenario, visualize it more in a permission blockchain scenario. In a permission blockchain, many transactions are being done by various nodes in the network, and you need to pool these transactions and get your block accepted. So to pool these transactions, since we are not using proof of work, we are using some mechanism where we are electing some leader, some delegate, and asking him to validate our transactions. Now, what is the job of that delegate? He has to pool the transactions. He receives one transaction from me, one transaction from you, and one transaction from another user. A very naive idea of pooling these transactions is first come first serve. Whichever transaction he receives first will be kept in the block first. But in a distributed system where synchronization is a very big issue, how do you order these transactions? How do you pool these transactions in your block? So you need to set some rules for ordering the transaction. Hyperledger Fabric has its own rules on how to do ordering the transactions. In fact, it follows an algorithm to order the transactions known as raft algorithm. Earlier it used to have Kafka as an ordering algorithm. Now Hyperledger Fabric is using raft algorithm. So what does this consensus algorithm, practical Byzantine fault tolerance algorithm, do in consensus mechanism is that this works on a three-phase manner. In the first phase, you have to select a node where it is basically selecting a delegate sort of thing. We don't use the word delegate, but you need to select a leader sort of thing. So when will you become a leader is that if it has received votes from over 2/3 of all the nodes. So why over 2/3 of all the nodes? To avoid this malicious nodes in the network, we use this votes from over the majority thing basically. It requires that every node is known to the network, and Hyperledger Fabric basically utilizes this so that it can handle at least 1/3 malicious nodes. But if it has more than 1/3 malicious nodes, the network is about to collapse. Once a leader is selected, then that leader will take the job of ordering your transactions based on some ordering algorithm, and then your transactions get committed. Then Ripple is another consensus algorithm used in the Ripple network, where again, what does this particular Ripple do is that it will use something called collectively trusted subnetworks within the large network. So what it will do, it will have a server, it will take help of a server for participating in the consensus process, and the clients are only for transferring funds. In the sense, client is one who will be participating only in the transactions, but for the consensus process, you have the leaders. We call them as servers in some algorithm, leader in some algorithm, delegate in some algorithm, but their job is to pool all the transactions in some acceptable fashion and commit them in the blockchain. So this particular server in this algorithm, it maintains a node list, unique node list identified by the respective node IDs. And this, the server, what it will do, it will query the nodes in the node list that you have kept to put a transaction. If 80% of the nodes agree that it will be allowed, you will keep it in the block for the committing purpose. I think we have enough number of consensus algorithms. What is it that we need to consider when you are looking at a consensus algorithm? Imagine now that you are proposing a blockchain. What are those factors? There is nothing like this algorithm is good or this algorithm is bad, but you need to understand that when we are proposing a consensus algorithm, you need to identify or you need to understand the purpose of that particular blockchain and the domain in which that particular blockchain is being utilized. So these are a few parameters that are identified by Monrad and Shilin in their survey paper, where identity management of the nodes. So proof of work, proof of stake are used in public blockchains. That is why there is no identity management. It is open for all the nodes in the network. Whereas practical fault Byzantine tolerance and tendermint, these are used for public blockchains. Energy consumption, proof of work is the worst among all the consensus algorithms. Its energy consumption is so high that people have to look for alternatives. Proof of stake is low, but as I told, we have this problem of rich getting richer. And the others are much lower. So adversary tolerance is that how many malicious nodes can you tolerate in your network. So it differs from algorithm to algorithm. In the at least the Byzantine fault tolerance one, it is 1/3 of the nodes. So if more than 1/3 are malicious, your network is going to collapse. But proof of stake has interestingly resistance to 51% of the nodes in the network. Scalability in the sense how many nodes can you add to your blockchain? How many nodes can participate in your blockchain network? So the study shows that almost all consensus algorithms are scalable when the number of nodes increase in your blockchain, except that Byzantine fault tolerance, because Byzantine fault tolerance cannot tolerate more number of malicious nodes in the network. And then performance is again another reason. If you are using it for if you are using it for a security purpose, your blockchain, you need to look at adversary tolerance. But if you are using your blockchain in a supply chain management, where it is not more about security, but it is more about performance, supply chain logistics, right? You need to deliver the product to the destination in a much efficient manner, right? That is where performance matters. So the performance here is calculated based on the number of transactions that get committed per second. And proof of work is very low when it comes to performance. It is because number of people participate in the consensus in a public blockchain, and when the number of nodes are high, coming to consensus becomes slow. Whereas permission blockchains, you are able to see that the number of transactions per second are high. How many of these consensus algorithms result in a forking? When two nodes are able to find the same nonce at the same time, you can have a fork in proof of work. Proof of stake, it is very difficult to find a fork because you have to find two nodes who have equal amount of higher number of stakes. That combination is difficult because it is not only the higher number of stakes, we are also saying the age of the stakes. So such a perfect combination is difficult to find. So you may not have a fork in proof of stakes. Fault tolerance, Byzantine fault tolerance, you may find a fork, but for the others, it is hard to find a fork. Consensus confirmation time is high because this is again connected to your performance. If you have less transactions, your consensus confirmation time will be high. Whereas if you have more transactions, it indicates that you are confirming more transactions in less time. Block creation speed is slow. It is obvious in public blockchains, and it is fast in permission blockchains. And these are the examples. So when it comes to applications of blockchain, now you can find applications. This is the part I would like to focus. You can apply blockchain in every damn application in the real world. You name anything: healthcare, IoT, supply logistics, finance, voting, insurance, anything. Anything you can apply blockchain. But remember, blockchain is not for security, blockchain is for transparency. You are not going to it is mainly for transparency. We say it is a decentralized network. It is works in a peer-to-peer fashion, and to have it, it maintains a ledger which is tamper resistant. So to show some transactions which are tamper resistant, in the sense you are maintaining transparency among the transactions, no one can alter them at any given point of time. That is what you are going to achieve in blockchain. But added to that, if you want to have security, you can have some more additional things. People in who are doing research can do research in those respective directions. But to do research in those respective directions, now we'll come to the core part of our talk, which discusses about the challenges in blockchain, especially the security and privacy challenges in blockchain. May I request the organizers for a 5-minute break? Can we have a break?
Yes, ma'am.
Yeah. So, can we have a break now?
Yes, ma'am. We can have a break now.
So, right. So we'll come back after.
Dear participants, we will have a break for 5 minutes.
Right. So we'll come back after.
Ma'am, 3:25.
Sure, sure. Thank you. Sure, sure.
Yes,
Thank you.
3:25.
Rekha ma'am, sorry to interrupt you.
Yes, ma'am.
Yes, ma'am. Shall we go for a break for about 5 to 10 minutes?
We are already in break, Sirisha.
Okay, you're all right, all right. Yeah, yeah.
Someone have
Okay.
already announced a break.
All right. Yeah. Thank you.
So I'm back. Shall we start?
Ma'am, actually, some of the participants, they were asking for a 10-minute break.
Oh, no
So
problem.
can we
Can you
start
just
at
ping me once the break is
3:35?
Okay, can you just ping me once the break?
Yes. Yes, ma'am. Yes, ma'am. 3:35.
Can you just ping me? Okay,
Yes,
fine.
ma'am. I
Thank you.
will.
Thank you.
Ma'am, we can start.
Okay, sure. Okay, sure.
Yes.
This meeting is being recorded.
So coming back, we will see those challenges in blockchain that, especially if we have to work on blockchain, if we have to choose a blockchain, we have to look at those challenges that are being faced. Blockchain is a very good, it's a very good area where we can start working and all. But then, if we want to work with blockchain, what are those things that we need to concentrate, that we need to take care of, especially when you are opening this blockchain on a really large scale, on a big network, and across all the stakeholders of your organization, for example. So these are the major challenges that we can categorize in blockchain, collected from various surveys that were done from people who are working in blockchain. Scalability, selfish mining, energy consumption, interoperability, and lastly, the security and privacy itself is a major concern in blockchains. So scalability, why is it such a concern? Why scalability is such a concern? See, especially when you are using blockchain, Bitcoin, especially Bitcoin blockchain being a public blockchain, scalability cannot be anticipated because anyone can start joining the network. And when more nodes start adding to your network, will your blockchain be able to handle that? What are those things that you need to face? Right. Blockchain size is 1 MB. It's no longer 1 MB. Now the size of blockchain have increased more than one. It's the average size of a block in a blockchain. It have gone beyond 1. It's more close to 2 point something. And the entire Bitcoin blockchain itself has exceeded 267 GB storage. This, you don't believe, this is a very old data. 269 or 270 GB storage is some data that we have around 2 years back. Right now, the blockchain size is close to 392 GB storage. If you talk about Bitcoin blockchain, any idea what is the blockchain size of Ethereum blockchain? The blockchain size is 9 TB. Because Bitcoin blockchain is limited, the usage of Bitcoin blockchain is limited to crypto transactions itself. Whereas Ethereum blockchain has expanded its origins, it was being used in businesses, it is used in enterprises and all. So smart contracts have really pushed the limit of the usage of Ethereum blockchain in many applications. So right now the blockchain size was 9 TB. And the mining time per block, it takes around 10 minutes for Bitcoin blockchain. And the rate of transaction is 7 transactions per second. Again, this was very old data. Now it was able to do more number of transactions per second, 13 transactions per second. But still, it is incapable of dealing with high frequency trading. All the credit cards that we use in our Amazon and Flipkart and Myntra shoppings, they which are having this very sign as a trusted third party, they will be carrying around 1300 transactions per second. So 13 transactions to 1300 transactions is a huge gap based on the rate of transactions. Why is Bitcoin blockchain very slow? It is because of the size of the blockchain size. It is because of the size that it. So there is always a trade-off between block size and speed. And when you are choosing your blockchain, look at what is it that you are more focusing on the block size or the speed, because both of them are inversely related. You want to increase the speed, decrease your block size. If your block size is a concern, speed should not be affecting you. So that is how you will be dealing with. But then when I have so much large, heavy size blockchains, what are the alternatives that I can look into in the future? 9 TB is the size of your blockchain size. So if I want to have Ethereum blockchain on my system, I should be able to accommodate 9 TB space on my system. Although now all the systems are coming with heavy capacities, 9 TB is again a big number for the normal systems. So what are all the alternatives that we have in literature is that storage optimization of blockchain is one idea. What we do in this storage optimization is, I'm just basically giving you a basic idea of how it works. If you are really interested in, you can go and look into the respective papers. The old records that are there in the network are removed. And what you do is that a database to hold the balance of all these addresses is maintained. So what you don't have a copy of every transaction that was done on the Ethereum blockchain will be recorded. It only says, especially when the old records. So for this public key address, this is the balance on so and so data. For this public key address, this is the balance on so and so date. And only that database will be maintained by the blockchain. And the other alternative or one more idea in storage optimization is that people are opting for lightning networks. What are lightning networks is that lightning networks are those networks generally in a business scenarios when you are trying to make a deal with a other party. How does it go is that your deal don't get confirmed in the first iteration itself. You propose some value, the other opponent proposes some other value, and after some series of conversations or after some series of transactions, you come out with one single payment deal, right? So what these lightning networks offer you is that they will allow you to do all these micro transactions onto a offline client, and only the final transaction will be put on the blockchain, thereby lessening the burden on your blockchain network. Lightweight clients are also another option where you can outsource your expensive computations to other servers, and lightweight clients only maintain the database which is having the address of all these balances. So when there is expensive computation that you want to outsource, you will send it to multiple servers and you will ensure that the correctness of the server is correct by comparing the results from these multiple servers, and you will take the majority value that was given by the multiple among the servers. Another option for scalability is that you can altogether think about redesigning the infrastructure of the blockchain itself, where you entirely redesign the blockchain into two parts. One is a key block for leader election and the micro block where you can store transactions. So what happens is that the micro block will be focusing only on doing the transactions, whereas key block is for the leader election part. He will collect the transactions, he will validate them, he will commit them and all this. So the miners will compete to become a leader, and leader will be responsible for this micro block generation. And this leader will not be a permanent fellow. For every new block, you will have a new leader based on some criteria. It can be proof of stake, it can be proof of authorization, it can be proof of deposit. How you want to do it can be worked out in the respective blockchain. Selfish mining is a major challenge many blockchains are facing. Why do people do selfish mining? Basically to achieve larger revenue than their fair share. What is the actual revenue that you get in your blockchain transaction is that the mining reward that if you win the mining round, and the transaction fee of the transactions that are there in the winning block. So both these put together will be your revenue. But if you want a share more than that, people opt for selfish mining. What do they do? How do they do selfish mining? Selfish miners, what they do is that when there is a fork in the block, generally all the peer nodes will be adding, all the miners will be adding blocks to a particular node. Suppose say 3A and 3B are a fork that occurred at node 3, or sorry, at block 3. So selfish miners keep mining their blocks to 3A, and all the rest of the miners will be keep adding their blocks to 3B. So what happens is that when the rest of the miners are adding to block 3, there is more competition to add to block 3 and less competition to add to block 3A. So these selfish miners keep their mined blocks with less competition and they don't broadcast them. They'll simply start adding a private branch, and this private branch will be revealed to the public only if sub requirements are satisfied. What is that one requirement is that among the two folk, when there is a split in the blockchain, whichever block has larger size will be accepted as a public blockchain. So among the split in the fork, whenever this private blockchain becomes larger than the public blockchain, then it will be made public. Till then, they don't propagate it. Right? So what happens? The private branch becomes longer than the current blockchain, and then it will be made public and it will be admitted by all the miners. What is the disadvantage that we have is that honest miners will waste their resources on 3B, on a useless branch, because now even the transactions are committed, they will go back to the pool, and selfish miners will mine a private chain with less competition. There is no honesty in the mining process at all. So that is one problem with selfish mining. So what can be done? What can be the possible solutions for selfish mining is that, or even before that, what can eventually happen in selfish mining is that, so these people who do honest mining also get attracted to this selfish mining pool, because obviously they are generating larger share, they are getting more money, and eventually this selfish mining pool will become more such a large size, they will cross that 51% computing power of the overall nodes of the network. And when they cross that 51% of the computing power of the overall nodes of the network, they can reverse the transactions that happen in the blockchain. So to avoid that, what can be done, or what was already being implemented in the blockchains is, in addition to the block that was being propagated after the mining, we are adding random values and timestamps, where once a block was block was generated, they can propagate it within a time interval, and if your time interval has elapsed, your block is not going to added in the blockchain. That is how you work, but the problem is that timestamp can again be forged. Interoperability is another major challenge in blockchains. You go to GitHub, GitHub has more than 8,000 blockchain projects that are there, which are isolated. The reason for being isolated is that there is no standard protocol where the industries can come together, collaborate and integrate with each other. For all many major programming languages, you have such standard protocols and platforms to do so. But however, blockchains are supporting only very few programming languages thanks to the latest versions. Earlier, you used to, the people working in blockchain need to learn Solidity, Go programming languages to work in blockchain, which are not so popular. And then now, slowly we are into JS, Python is being acceptable in programming languages. And because of this no standard protocol, blockchain developers who are working in different programming platforms, they are remaining isolated because they don't get help when they are stuck up and all. And standardization is still an issue in blockchains. Energy consumption is a major concern in blockchains, especially when you are using public blockchains with a consensus algorithm like proof of work. The loss is that consumption of massive amount of energy and extreme carbon footprints are released onto the world, especially we have examples from coal-fired power plants in China providing a lot of fuel for the Bitcoin mining networks. The gain, what is it that we gain from this proof of work consensus is that we have eliminated the need of an intermediary third-party cost, but the cost that we are paying is too high, isn't it? So what is the trade-off? Are you ready to bear so much cost to remove that intermediary, or you want to go for an alternative? People are looking at options for redesigning the infrastructure blockchain. They are looking for alternatives for proof of work. Many many consensus algorithms that we have discussed, such as proof of stake, delegated proof of stake, are already there in the literature where they are consuming less energy. In fact, Ethereum itself has set an example by moving away from proof of it was in the process of moving away from ET hash to Casper. So security and privacy as it is a big area in blockchain where many concerns are there. So these are the major security issues that we look in blockchain. However, they are categorized into red and blue colors for our own identification purpose. The security issues in red color are those the generic security issues irrespective of blockchain domain. If you look at if you ask any person who is there in security and you ask for security parameters, these are the major parameters that will come into light: confidentiality, integrity, availability, anonymity, and authorization. Apart from that, the way blockchain was implemented, there are a few security issues leading to consistency, double spending attacks, pseudonymity, 51% attack, and unlinkability. Let us go into the issues one by one. This is a, I am not going to say that these are the only solutions that we have in literature, or a problem cannot be solved in blockchains. Blockchain being the baby of computer science world, there are no specific solutions that are standardized and says, okay, these are fixed and you can use them. Right? People are exploring the options, and especially for students who are in the project and who are doing their research can explore more areas into more issues, privacy and security issues in blockchain that can help for the overall development in the blockchain area. So one major issue that we face when we are looking at blockchain is the consistency. What is consistency in terms of blockchain? The consistency expectation that we have is that all nodes will have the same ledger at the same time. I told you this is a public ledger and that was being shared by all the nodes at the same. Now the expectation theoretically is that when every node is sharing the global ledger, all nodes have same ledger at the same time. But in reality, in practicality, when you try to implement blockchain, the reality error is that there are a lot of errors and inconsistencies between the ledgers that are held by different organizations. Why is it so? Why can't a ledger be maintained in a same copy across the institutes? Various reasons. The architecture and business process among the institutions vary. There can be involvement of manual process. So when a block is being added to the blockchain, by the time it gets reflected in the global ledger and from there to the copy of the actual node, will have many hiccups. So the organizations have to choose what type of consistency do they need in their blockchain. Is it an eventual consistency that they are looking into, or a strong consistency that they want? Why should I look for a type of consistency? Because you can't have both. And depending on the domain where you apply blockchain, you can opt for what consistency you want. Eventual consistency is trade-off between availability and consistency. So in the sense that if it is available, if the data is when it is propagated to the other nodes of the network, it will take some time for update. There will be network delay, there will be node delay, there will be many possible reasons. So if someone reads the data from a replica which is not yet updated, probably some network issue, some delay, there is a risk of returning stale data, old data. So the key challenge in eventual consistency is that how to remove the inconsistency that may be caused by stale data. So in eventual consistency, your data is always available. However, there may be chances that the data you read may be a stale data. Strong consistency is a trade-off between availability and cost. Here, all the nodes will ensure that they have the same ledger at the same point of time. And when the ledger is being updated with any new data, all the nodes we have to wait for the commit of that update. So when you are ensuring that all nodes having same ledger, same point of time, the key challenge is that you need to have so much amount of computational resource. You cannot afford a system failure, you cannot afford a malicious node, you cannot afford a power failure, network delay, all these things. So you need to have so many backups, you need to have plan B, you need to have other routing algorithms and all. So the performance cost will be high. So your data should be available, but is it a stale data or old data? You doesn't mind, you go for eventual consistency. You can't risk for stale data, opt for strong consistency, but however, you may need to pay more in terms of you have to pay more cost when you are maintaining such a blockchain. That is in terms of consistency. Then availability. Availability is a major issue. There can be a lot of attacks, DOS attacks, DDoS attacks. Many types of data attacks can be there in the blockchain because it is being maintained on a network. It is no different from any other network maintained systems. Now, when I say availability is a major security issue, in the sense because your ledger should be available to all the nodes in the network. When I talk about availability here, I talk about two things: availability of the system and availability of the data. Availability of the system is that availability of the blockchain, the ledger, and the data is the transactions on the ledger. So users should be able to access the data of transactions at any time, any place. And as I said, the blockchain should be available. At the same time, the transactions on the blockchain should also be available. Existing literature with respect to availability of systems and data will be helpful in addressing these problems. Integrity. Integrity is that miners may, not only miners, malicious nodes even may attempt to tamper with the information of the received transaction. So X sends $100 to Y. So the destination receiver may be changed from Y to A, $100 may be modified to $1,000. Anything can be tampered in the information of the transaction. So how can we address this problem? The best part in blockchains is that you don't need to address this problem because the blockchain setup itself will take care of that. The collision resistance property of SHA-256 algorithm and unforgeability nature of the signature algorithm, elliptic digital signature algorithm used in Bitcoin blockchains ensures that your data remains tamper resistant. If you change I told you in the beginning itself, if you try to change the 1 bit value in the transaction, it happens to alter so many other blocks. So what is the big deal? I'll replace it with a reasonable hash. But the problem is that you cannot find an equivalent input which will match with the same hash value. Similarly, you can't forge the signature algorithms used in the transaction validation and verification. So adversary may try to tamper the information and tamper the transactions that are stored on the blockchain, but he has to modify a lot of historical data, the hash pointers on the distributed ledger, which is highly infeasible at this point of time. So rest assured, integrity is completely achieved in blockchains. So all the transactions that are stored on your blockchain are tamper resistant. Double spending. Double spending is a major issue. Double spending attack is a major problem in blockchains. What is a double spending attack? Imagine if you have 100 rupees and I have to pay 100 rupees to another person. What I do is that I give this 100 rupee note to that other person and it indicates that I have paid to that person. Right? So, and now if I want to pay another 100 rupees to another person, I cannot do it in the physical world because I have already given this 100 rupee note to the first person. However, in a digital world where the money you have is identified by the numbers on the system, the same digital cash can be spent more than once. A transaction can be modified, a transaction can be replayed. The digital file can be duplicated, it can be falsified and all. So what will happen in such a scenario is that the same 100 rupee digital cash can be spent in 2 different transactions. Whereas although you have 100 rupees in your wallet, you are able to do the transaction twice because of the duplication of the digital file. So the combination of the transaction signed with your digital signatures and the public verification of the transactions with majority consensus followed by timestamps. All these ensure that the double spending attack do not happen on a blockchain environment. Are in there scenarios where double spending has happened in blockchains? If you look at the real-time data, if you look at the internet where double spending attacks are there in blockchains, there are CEOs who have lost so many dollars in the double spending attack. But then, based on the attacks, blockchains are also developing. They have improvised their digital signatures. They have improvised their consensus algorithms. They have introduced new parameters such as timestamps and all to ensure double spending attacks do not happen on their blockchains. But are they the final solutions? I say no, because the wiser the designer is thinking on not allowing double spending attacker, the harder the attacker is trying to pose a double spending attack. He is finding loopholes, he is finding additional possibilities on how to do a double spending attack. So if you are really interested in that part, that is a great area on how to ensure double spending attacks do not happen on Bitcoin, on blockchains in general. Bitcoin blockchain, it is completely resistant. Double spending attacks do not happen because it was built in such a way that it maintains certain lists where you cannot spend a coin more than once. But in other blockchains, the scenario is not the same. There are scopes and loopholes where double spending attack may happen. So people can work on that. 51% attack. 51% attack is that attack where some group of miners come together and perform a conspiracy. What can they do is that when this group of miners computing capacity crosses 51% of the total capacity, computing capacity of the network, they may be able to reverse certain transactions. They may be able to reverse certain genuine transactions. They may be able to do undo certain things. The so-called tamper resistance that we have proudly said in blockchain earlier may not be feasible anymore if 50% attack was possible. So we need to ensure that your system is resistant to so-called 51% attack. How do we ensure that? We need to ensure that the so-called miners should not come together, should not come together so that their capacity increases by 51%. But in scenarios like selfish mining, where the miners come together to do some conspiracy, dishonest mining and all, this 51% attack may seem to be a reality. People are looking for so many possible options to avoid 51% attack. But you can open the blockchain explorer and see. You can open the Etherscan explorer for Ethereum blockchain and see. Blockchain explorer is for Bitcoin blockchain and Etherscan is for Ethereum blockchain. If you see who have mined the very recent blocks on the blockchain, there will be only a couple of names that will be repeating again and again. In the sense, we have already started seeing that pools are happening. Miners are coming together and forming a mining pool because one cannot afford the entire computation. Miners are coming together, sharing there are already mining pools available because they are coming together, sharing their workload, and then if there is a reward for them, they are also sharing the reward. But if these miners collude together and become a majority, in the sense if they can cross that 51% of the total computing facility, the problem is that they may reverse some genuine transactions, and there is a lot of research happening on how to avoid 51% attack. The next security and issue is anonymity. What is anonymity? Anonymity is that if somebody in Bitcoin blockchain, users are able to do the transactions and users are identified by their public key addresses but not with their original identities. So you can have a peer-to-peer transaction without knowing who the other person is, and trust is built within the mechanism. So the disclosure risk of user's identity by some intermediary. So this public key addresses, as long as you make any transactions, they are not able to find out who this public key address, public key is related to. But if there is a risk of disclosing the user's identity, then it is a risk to your anonymity. So in scenarios, why should a user be worried about not disclosing his worried about disclosing his identity? Suppose, say, my medical data is a very sensitive data among all the data. So if that data is kept on a blockchain, and if somebody is trying to figure out who this user is, somebody have these symptoms. So if you are trying to reveal their identity, then that is a very breach to the privacy of the user. This is one privacy breach that is identified in blockchains. So what is it that we can do? See, medical data, COVID data, and financial data. Many users are not willing to reveal their financial transactions and financial data openly. Okay, if there is an income tax person who wants to verify, he can verify your transactions, but I'm not willing to reveal all my financial transactions to everyone in this world. Okay, in such scenarios, what will happen? It is a real breach of anonymity. It is a privacy issue where your identity is revealed. We call it as identity privacy in blockchain, a state of disguised identity. So in actually blockchains, you don't have a complete anonymity, but you have something known as pseudonymity. So pseudonymity is a state of disguised identity. People may not be knowing you, but they know your public key addresses. The only thing is they know the public key addresses, but they don't know to which original ID these public key addresses match. Then unlinkability also. When you have, I have multiple pseudonym addresses on my blockchain, but if I can provide some linkability among these multiple addresses, then people can be able to trace my transactions. So every transaction that is there on the blockchain is recorded with the sender's address, receiver's address, and the amount is traceable, because every transaction has a transaction ID and the public key addresses of sender and receiver. If you can pool all the transactions that happened on a day, which are publicly available on the respective blockchains of those. If you want the transactions that happened on Ethereum blockchain, they are available on etherscan.io. If you want to look at all the transactions that have happened on Bitcoin blockchain, they are available on Blockchain Explorer. So you take a list of all the transactions happened on that day, and if you can run a simple statistical analyzer on those addresses, you can relate the users and the transactions. We have many techniques to de-anonymize the user. We are saying the user is anonymous, but there are many techniques which will de-anonymize the user. Network analysis, address clustering, transaction fingerprinting, DOS attacks. People who are into ethical hacking know how to use these techniques to find the relation between the user and his transactions. So the full anonymity of a user can be protected by having both pseudonymity and unlinkability. Pseudonymity alone will not give you anonymity, but if you can have unlinkability also added to that, you can help in achieving full anonymity. So the next thing is confidentiality. What do you mean by confidentiality? confidentiality is that security feature where we say that the content or the transaction content is private. So thereby the transaction information cannot be accessed by any unauthorized user. Is it the case in the existing blockchains? No. Let us see. I'll show you probably, just give me a second. Look at this website. Etherscan.io is that website which will show us all the transactions that happen on Ethereum blockchain. So if you look here, this is the latest block that was added 21 seconds ago. And these are the latest transactions that are there in the unconfirmed transaction pool. So, in the latest thing. So, these are 101 transactions that are added in the very recent block. If I click on that 101 transactions, it will show me all the transactions happened where this is the hash value of the transaction. And these are the firm and true addresses of the respective transaction. If you look at this picture as it is, if you look at the screen as it is, I definitely cannot make out to whom the transaction was done. But if I can download them as an Excel sheet, figure out who are having the same public key addresses, I can apply filters and all on a normal Excel sheet. I'm not telling all the techniques that I have told you. On a normal Excel sheet also, we can say how many transactions are made by a public key address on a given day. Now, in such a scenario, imagine with all the techniques that we know, as I told you, all this network analysis, address clustering and all these things, you can obviously de-anonymize the user. Now, when I say confidentiality, I say transaction information cannot be accessed by any unauthorized user. But if you look at the Etherscan that I have showed you just now, what all you have on the screen is that you will have all the details of the transaction value, for how many ethers the transaction was made, from whom, from sender's address, receiver's address, and then the transaction fee that was paid in the transaction. All these things will be already accessible by any user of the network. So is confidentiality a real concern? It was a tricky answer to say, because in general, the system admin or the participant of the network cannot disclose any user information to others without his permission. But here everything is there on the blockchain itself. Right? However, the other concern we have is that user data should be stored and accessed consistently and securely, even under unexpected failures. A power failure happens, some network failure happens. Still, the latest user data should be available. Keeping all these things in mind, transaction content and addresses are public. However, transaction data and addresses are public. However, transaction content is private, because we assume that the public key addresses cannot be linked to the original IDs. But if they are linked to the original IDs, privacy leakage automatically breaches the confidentiality of your transactions. If I know if I can map a particular public key address to a particular user, automatically my transaction is no longer confidential. So confidentiality is a tricky question to answer. As long as your privacy is not leaked, your transaction is confidential. Once privacy leakage happens, transaction automatically becomes breach of confidentiality. So with so many security issues, are we still using blockchains? With so many concerns with respect to security and privacy issues, even before going to this slide, I would like to say, especially privacy is what I am working on. So we basically work on three major concerns. One is identity privacy, transaction privacy, and the third one is smart contract privacy, which is very popular because of the smart contracts being introduced in almost all the blockchains nowadays. So there is a lot of work going on with respect to these three privacies. If your identity is breached, automatically your transactions are breached. Even if my identity is not breached, I want my transactions to be confidential. I have certain mechanisms to do that. Okay, and then smart contract privacy is altogether a different world to work on. So what are the techniques that are already there in literature to overcome these concerns, privacy and security concerns in blockchain? These are a few techniques. I'll just give you a glimpse on how these techniques work. Let me see if you are interested in any of them. So when it comes to privacy threats, one is identity privacy, the other is transaction privacy. Not only these two things, smart contract privacy is the recent addition that was done. So what is it that identity privacy requires is that there should not be any tractability between the transaction scripts and real identities. So there should the transaction relationship between the users should not be there is what identity privacy requires. Transaction privacy, transaction contents can only be accessed by specified users. You may not relate them to identity, but still, see, imagine some applications like health data, health records and all. If a particular person finds out that there are no more number of COVID cases in a particular area, no identity is revealed, but still that is a breach of confidentiality of the information. So what are the techniques that are related is that mixing techniques are very popular in literature when it comes to protecting the transaction relationships, transaction privacy. They try to obfuscate the transaction relation with help of a mixer. What does this mixer do is that a similar thing that like the mixer that we use at home. What we do, we keep certain ingredients in the mixer, and when you switch on, all of them will be mixed together, blended together, right? So the mixing services also do the same, where they exchange user coins with other user coins and obfuscate the user ownership. What is it that we don't want the attacker to know is that X sends a transaction to X makes a transaction with Y. So X makes $100 transaction with Y, right? If $100 are sent from X wallet to Y's wallet, we will be able to find that relationship. However, mixing services, what they do is that they will pool certain number of transactions. They will pool transaction of X, A and B, join all their money into some pool or wallet, and from there they will send to Y, R and S, some other three users. Thereby, this direct connection between X and Y will not be established. So mixing websites offer to mix transactions anonymously. So there will be this one mixing service or server. We send our money to them and they send to the respective user by mixing various such transactions. Concerns with respect to centralized mixing services is that they may steal our user assets by not transferring them. We don't know how we trust them. So the solution is that conditional execution is there. You can keep the log, and these centralized mixing servers themselves may keep log information to route the transactions and all, and if that log data is revealed, again you can be able to establish the transaction. Delay will be there in the transactions because you have to pass to the mixing server, and mixing server have to join certain transactions, mix and then send. So there will be obviously delay in the transaction. And single point failure is also there because there is only one server that you are relying on, and the fees that was has to be paid to the server is also high. Then comes an alternative, which is decentralized mixing service, where you make a joint payment together, but you don't rely on that centralized mixing service. You have some untrusted piece, they publish their transactions simultaneously, and the mixing happens without a need of a third party. But how do you establish the trust the same way we have established trust in Bitcoin blockchains. Advantage is that you can avoid that centralized structure. Anyhow, we have decentralized structure in blockchain that is compatible with this decentralized mixing services. You can avoid the mixing fees, malicious nodes. Even if they try to get the relationship between the transactions, they'll not able to get it. Okay, however, it has its own risk also. The thing is that if there is an attacker in that joint payment, he may refuse to sign the transaction, because when multiple people come together, you have to do a multi-party computation, which if one of the attacker refuses to sign, the entire transaction gets delayed. And then communication overhead will also be there to have a to establish that link between all these payments, to combine, join these payments together. Another solution that we have already in literature, this is not offered in blockchains, but cryptography have this since a long time, that is anonymous signatures. Under anonymous signatures, we have two types of signatures. One is group signatures and the other is ring signatures. Group signatures, what do they say is that any member of the group can sign a message anonymously by using his secret key. So if some 50 people are form a group, we have one single group signature, and it's not that same signature is used by all of us. Each of us can use our own private key, but with help of some other parameters can generate a group signature, which can be sent by using my private key if I am signing it. And any member with the group public key can check and validate the signature. So the beauty here is that no one knows who have signed the signature, but they can verify the validity of the signature. So anonymity can be protected in these anonymous signatures. Signature verification, it will not reveal anything about the true identity of the signer, but however, your signature can be validated. And if you are trying to use these group signatures in consortium blockchain, you need to have a setup for group manager. One of my PhD student is working on these group signatures to achieve identity privacy in blockchains. Then we have ring signatures, where ring signatures are also anonymous signatures. The thing is that the same thing, member of a group can sign on behalf of the group, anyone can verify the validity of the signature and all. Only thing is that if at all there is a dispute that arises, in ring signatures, you cannot figure out who have signed that particular document. For example, say all of us have formed a group and we are proposing certain transactions, or say we are proposing some statements, and whoever is making agree with that statement will sign on that signature. Nobody needs to know who have signed on it, because any of us can verify the validity of the signature. But what happens if there is a conspiracy that arises, and if we have to figure out who have signed on that signature, ring signatures, you have no mechanism to find out. The probability to find out is 1 by n. If 50 users are there, the probability that a person X can be the real sender can be 1 by 50, which is very difficult to figure out. Group signatures, the group manager can help you to figure out who can be the signer. And ring signatures, also you have ring traceable signatures, where they can help you if there is a case of dispute. So this is what it says. Then we have homomorphic encryption that can be used in blockchains for the sake of security. How can you imagine homomorphic encryption? You all know what is an encryption, right? But homomorphic encryption is slightly different. That you can imagine it as a black box that ensures the operations performed on the encrypted data, on the ciphertext, and the original plain text will be generating identical results. See, when in general in encryption, when you convert that into ciphertext is in general a nonsensical data. If I want to perform a search operation, suppose I have saved a very confidential file on a cloud, right? and I want to search a particular line in that confidential file, and that file was saved in an encrypted format on the cloud. I have two possible things: decrypt there on the cloud and then search it, but that reveal the entire contents of the data, posing some confidential risk. Or download the file and search it on my own system. Right. Homomorphic encryption helps you, right, where you don't need to decrypt the data, but you can perform the search operation on the encrypted data itself. And whatever results that you get, you take the results and decrypt it on your system. They are equivalent to the actual results that you do on a plain data. So data on the blockchain will be encrypted, addressing the privacy concerns, but it allows ready access to encrypted data for auditing, so on, anything. You can perform research operation, you can perform computational operations and all. Ethereum smart contracts provide homomorphic encryption on data. Why do they use homomorphic encryption? Is that smart contract, once it was uploaded on the EVM, Ethereum virtual machine, it cannot be subjected to changes. And if malicious attackers try to change it, that may collapse the entire network, or at least few of the nodes in the network. That is the reason, to avoid such things, they use homomorphic encryption. Attribute-based encryption is also another similar thing, where if your attributes match, you will be able to get the thing. Then I have multi-party computation, which is also another solution for the security concerns. So what is multi-party computation is that this protocol, when you use a multi-party computation protocol, it will allow them to carry out the computation jointly by giving various private data inputs, but their privacy is not compromised. So even if a malicious node or an adversary tries to figure out from that computation, he learns nothing about the inputs of the authentic party. He only knows what the inputs are there, but he doesn't know who the users are. He doesn't get any information about that. So multi-party computations have been used in blockchains to protect privacy. And zero knowledge proofs are used for privacy preserving in cryptography as well as in blockchains also. So one of my MTech student is also working on these zero knowledge proofs, where the idea is to achieve privacy. He is trying to use zero knowledge proofs on Ethereum blockchain to achieve transaction privacy. So what is this zero knowledge proofs is that you can prove a given statement to the, in a zero knowledge proof, you have two users, a prover and a verifier. Prover proves his statement and verifier need to verify the statement without leaking any additional information about the knowledge of the statement. For example, I am the prover and one of you is a verifier. Then I prove to you that I know the password for something. Okay. What is the direct way of proving it? I tell the password to you. But zero knowledge proof, as the name indicates, that I should give zero knowledge about that respective secret. So I will not reveal anything about the secret, but I will convince you in such a way that you can verify that I have the knowledge of the respective secret. So a certifier can prove himself to the verifier with zero knowledge and no interaction. Here also you have two possible things: interactive zero knowledge proof and non-interactive zero knowledge proof. To achieve privacy, blockchains are promoting non-interactive zero knowledge proofs. One of the protocols, ZK-SNARK protocol, zero knowledge, second non-interactive argument of knowledge, ZK-SNARK proof is very popular in blockchains to verify transactions while protecting the user privacy. Then smart contracts, which are being used in across various blockchains, there is a very great concern on how to protect these smart contracts that are used across the various blockchains. What happens? I have to smart contracts is that some logic code that was kept on the virtual machine of the blockchain. Everybody can access this. If I give wrong inputs, or if I give if there is bugs on the smart contract, a malicious user can take advantage of those bugs and can can cause for invalid transactions on the blockchain. So we need some environment where we can verify the security of the smart contracts. One is the trusted execution environment. So trusted execution environment is a completely isolated environment for application execution. So your system runs as usual, but there is this isolated environment that is available in your system itself, which will function on your or which will work on your smart contracts. So other software applications and operating systems that are there in your system will not tamper your smart contract, and this smart contract can be tested for any possible bugs and logic issues. Then comes game-based smart contracts. Game-based smart contracts are a very interactive verification game where the user sometimes he doesn't even realize that he is verifying a smart contract. He will be playing a game in the front end, and back end what is being verified is the actual smart contract computational tasks to check if it was being performed correctly or not. So we can boast a lot about blockchains. We can say that it is tamper resistant, decentralized, it provides that things, these things. But there are, if not all, there are a few concerns in security issues in blockchains, and there is a lot of literature and research going on in the security direction of in the privacy security direction of blockchains. So if you are interested in research, yeah, there are many points where you can pick up, especially one possible application, one possible way of doing your project is applying blockchain in a particular domain. You apply in healthcare, you apply in IoT, you apply in cloud computing. That is one way where your project can be immediately functional. Another research way of contribution is that working on the core issues of the blockchain. I have discussed about security and privacy issues, but if you look at the other challenges like scalability, interoperability, there are also major concerns where a lot of research is there in that direction also, where you can contribute in such a way that the blockchain can overcome those security concerns. But despite all these things, do you think blockchain is free from all security things? Please remember that security is a myth. Either it is blockchain or any so-called secure environment. If your system is plugged to the internet, your system is no longer secure. The only way to remain secure is that keep your system unplugged and don't allow to attach any sort of additional drives, additional link to the outer world. But without all these things, there is nothing like being connected, right? So we need to live with these concerns, but only thing is that have those precautionary measures. Security is a myth. No system is 100% secure. Just ensure that we take the security, privacy concerns into issue, move on with them. And these are a few references I have used in my talk. Thank you. I'll stop my talk here, and I'm ready to take any questions if there are from the audience, please. Any questions from the audience?
Participants, you can put your queries in the chat, and you can even unmute your mic and ask your queries.
Okay, there are a few questions here in the chat box. I'll try to answer them first. What about version 3 and 4 BCT? Sorry, I didn't get you. But what I was trying to put a point at that point is that earlier Bitcoin blockchains are considered as first generation of blockchains, and then once Ethereum came into existence, from then on it was because blockchains are used for enterprises. it was considered as second generation of blockchains. I really need to check if a third generation and fourth generation are already there in blockchains. Do permission blockchain can have central server system? May have. It depends on how they implement it. Permission blockchain systems are for such scenarios where you have a centralized way of working, but you love the features of blockchain. So it can have a central system. How do mining works and how do they find new blocks? As I said, in permissionless, the question is, do permissionless blockchains have central server system? No, permissionless blockchains cannot have central server system. Permissionless blockchains are public blockchains and they work on a decentralized fashion. How do mining works and how do they find new blocks? I gave you various algorithms for mining. So proof of work, stake, capacity and all. Is there any central authority in blockchain in permissionless? No. How to pick the privacy literature survey in blockchain? Can you suggest some reading sites? It's a conflict of interest. Just let me share a screen for you. So where is that? Okay. Two of my students are already working on identity privacy and transaction privacy, and since the work was not published, as I said, it's a conflict of interest. I really can't share you about that. But reading sites, yes, my talk I'll share with your organization, and the references have the reading material for privacy and security related things. So this is a mind map that was drawn by one of my students with respect to blockchain privacy. We are focusing on identity privacy and transaction privacy. So as of now, this is a literature that we have, but as I said, smart contract privacy, we are not focusing because identity and transaction, they are a bit overlap things. We are focusing on that. This is the information that was shared by my student, but I'm really sorry I can't share it with you because for my own research interest. But if you want the material that is there, at the reference material is there at the end of my presentation, I'll definitely share it. The next question is privacy check. Heard homomorphic encryption is not implementable. Is it true? Can you suggest any resources on this encryption? There are a number of papers implemented on homomorphic encryption. The statement that homomorphic encryption is not implementable is not true. The reason is that any confidential files that we store on cloud environment, they follow homomorphic encryption, right? Because that is the most suitable encryption when you want to store your files on homomorphic, when you store your files on cloud environment, but still have access to them. So it is not implementable is not true. If you want resources, I really don't work on homomorphic encryption. If you can send me an email, I can definitely give you some material on homomorphic encryption. So, any more questions? What about 30% tax on cryptocurrency? What gonna be legalization of it in India? I think Nirmala Sitharaman is the correct person for answering that. Indian government have a lot of concern for legalizing cryptocurrency in India, considering the terrorist threats and the money laundering scams that we have already. Without even cryptocurrency, we have so many things. So they think that introducing or legalizing cryptocurrency will enhance those problems. So they are thinking a lot to legalize them to curb those. But because other countries are moving fast onto crypto transactions, to curb the usage of those transactions, they have kept this 30% tax. But will they make it legal, and what their form of legalization? Along with you, even me, all of us are waiting to see how they are going to legalize. We just need to see. I don't have an answer for that. What is going to be the legalization of cryptocurrency in India? Any more questions? That's an interesting thing, but don't think blockchains, the applicability of blockchains to cryptocurrency itself. People have started using blockchains beyond cryptocurrency. Many Telangana government, Andhra Pradesh government have already implemented blockchains in land records registration. Dharani portal is based on blockchains. I don't know what is the portal being used by Andhra Pradesh government, but they have also used blockchains in their land registration things. And Western Union money transfer, they use blockchains not to make currency transactions but to record their transactions. They are using blockchains. So it's not that this blockchain is used only for those people who are interested in financial industry or a cryptocurrency sort of thing. Now it is like an area where if you want your data to be secure in a transparent fashion, you use blockchain. So you keep health data. If a patient is there, you can imagine an application like Apollo Hospital or a Care Hospital using blockchains, because they have patients, doctors spread across the country. So anyone can access and verify their data. They can store their data by overcoming these privacy concerns and all. MTech project on blockchain technology, you can approach, but definitely you can approach, but we just need to see if our areas match. So my focus as of now on blockchains is, as I told you, I'm working very precisely on identity and transaction privacy itself. So if your interest is also the same, you can always approach me. Let me see how far I can help you. Medical data, health people are approaching a lot to use blockchains in their environment. IoT is another domain where people are looking for taking blockchain as a platform apart from cryptocurrencies. So don't limit yourself to cryptocurrencies or financial transactions alone when you are using blockchains. Meta blockchain. I am really not sure about this, but meta blockchain is again to address the scalability of blockchains, where rather than storing all the transactions, you just store the balances of the public key addresses in the meta blockchain. The original blockchain will be stored somewhere else. This is a very lightweight client where you store only the final balances of the respective public key addresses. And if you want to do a verification, that can be verified. But if you want to do some computation, you have to outsource it to some other servers. So, any more questions? Okay. So, with this session, I think I have given you a glance of what could be a blockchain, what could be the possible consensus algorithms that can be used in various blockchains, and especially the security and privacy concerns. Some security concerns are well addressed in blockchains, but some concerns are still in a literature scope where people are still building up literature on how to deal with those security concerns. Standardization level, we haven't yet come because, as I said, it's a very baby of the computer science world. Although Bitcoin blockchain came into 2009, the real push to blockchains came in 2013 when Ethereum was introduced with help of smart contracts, where we can use blockchain in any application. So let us see, give some 4 or 5 years more to blockchain and see if we can come to a standardization level for these blockchains. So with that note, I'll take leave. Thank you very much.
Thank you so much, ma'am. I shall give the vote of thanks.
Sure.
Thank you so much, ma'am. It was an extremely informative, enjoyable, and above all, it was a valuable session today. I would thank for the topics taken today by you on the various aspects of blockchain, that is the challenges in blockchain, security and privacy related issues in blockchain. Looking forward to meet all of you tomorrow's session, that is day 5 of this online workshop, engaging with another resource person. With that, I take a leave. Stay safe, stay healthy, and be productive. Have a wonderful day. Goodbye. Take care. I shall be sharing the feedback form in the chat window. Kindly fill the feedback and quiz before you leave. Thank you, ma'am. Yes, I have posted the links, feedback, and quiz for today.